Okay, so it's fine. Hello and very good afternoon, everyone. I'm Mohammad Tehrani, and I would like to welcome you all in the second session of the second edition of Water Wednesdays Vespers Webinars 2025. This is a sharing time, which is planned to be held a couple of times during the year, sharing the hydraulics and water relevant issues for those sessions where the speaker will not attend in person. Our webinars will be conducted in hybrid mode, and unfortunately, this is not the case. Each session will feature dynamic presentation lasting approximately 30 to 40 minutes, followed by an interactive 20 minutes of Q&A session. Before we go directly into the talk, a quick reminder for you to stay please engage. Feel free to ask questions using the chat box, and we will address them in dedicated Q&A session at the end of the session. Or you could turn on your mic and camera and ask it directly. Today is no exception, and we have a distinguished speaker who will share his expertise and insights on the titled From Models to Applications, Data-Driven Solutions for the UK Water Industry. Whether you are a pioneer, senior, or professional, or a just young beginner in this area, please get ready for an engaging and informative session. So without any further ado, let me introduce our speaker for today, Dr. Ehsan Kazemi. Ehsan is a seasoned civil engineer with over 14 years of expertise in numerical modeling of flow hydrodynamics and 7 years of experience with the application data analytics to enhance water system resilience. He holds a PhD in civil engineering and water engineering, specifically from the University of Sheffield, where he was awarded the prestigious Marie Curie Fellowship. Ehsan specializes in computational fluid dynamics, AI-driven data analysis, and software development with extensive experiences utilizing programming languages such as Python, MATLAB, and C++ to develop GIS tools and water quality analysis software. Ehsan currently works as a senior consultant at Intertech Metok and previously as a research associate at University of Sheffield. Ehsan has led multiple projects with the water industry and developed innovative solutions for water infrastructures, including AI-based flood warning systems, urban drainage management models, and water quality assessment tools. His collaborative research spans academic and industry across the UK and EU. And active contributor to his field, he has authored over 15 peer-reviewed journal papers, served as a guest editor, and developed open-source software for water system resilience. So, without any delay and ado, Ehsan Jan, thank you for accepting to be with us today. And yeah, the floor is yours. Ehsan Jan, can you hear me? Mhm. Unfortunately, it seems that we do not hear you well. Could you please check your mic again? Okay, now it seems that we can hear you.
Okay, so thank you for the
Perfect.
introduction. I'll go to my
You're welcome.
presentation if
Yes,
that's okay.
please. Yeah, sure. Please share it with us first.
Yeah. Share my sharing screen here.
Now we can see your page.
Yeah.
Perfect.
So let me check. Okay.
No worries at all. No worries at all. Take your time.
I think. I've got two screens. I think.
Yeah, I think you should choose the other one. That's true. That's true. And no worries. Take your time. We are still some guests who are joining us, so perhaps it would be even better. So we will have the other as well.
Yeah, that's fine. This here. No. I think. Yeah, let me.
I'm glad that I'm seeing there are newcomers who are joining our, let's say, session. So that's perfect. For those who are joining us for the first time, please feel free to comment or ask your question using the chat box. And at the end of the session, we will have the Q&A session, and we will address your remarks or question. And also, you could turn on your mics at that time and directly ask your question or share your comment with Ehsan. And by the end of the session, after the Q&A session, at the end, we will have the group photo. So if you would like, prepare and be ready for a nice group photo at the end as well.
Sorry about that.
No problem at all. No problem at all. Yeah, it could happen even if that we had the pre-session at early this week, and like just 45 minutes ago, and everything was working well. But yeah, it could happen. Yeah.
Yeah, it was okay. But, so let me try again. Share my screen. Let me make this full. I think it should work now. Right?
Now we have received it perfectly. Thank you so much.
Well, yeah, I changed. Sorry. I just changed my screen. And,
Okay. Yeah, that could be a reason. Yeah. Great. So, sorry for inconveniences to you, Ehsan. Thank you for accepting to be with us. So now the floor is yours. I will just turn off my mic and camera, and yeah, we could listen to your insights. And thank you so much for sharing.
Thank you. I'll start in a bit. Right. So. Right. So, good afternoon, everyone. Thanks for joining me today. I'll be sharing insights into two connected but distinct parts of water engineering in the UK, which are data analytics and academic research and environmental modeling in industry consultancy. So we will look at how these efforts contribute to solving practical challenges, especially in water engineering. So yeah, this talk will be divided into two main parts. First, we will explore academic research in water engineering in the UK, looking at how research groups are leveraging data analytics to improve water quality and infrastructure reliability and resilience. So I'll give examples of research that's been carried out specifically for industry applications in this part, and then I'll move into the consultancy landscape, highlighting how data is being used by industry in the UK to assess river water quality and manage the sewer impacts. So let's start with academic research. In the UK, the universities of Sheffield and Exeter particularly have been at the forefront of applying artificial intelligence to water engineering problems. So other institutions such as Birmingham, Leeds, and several others are also making significant contributions in this field. These universities, sorry. Yeah, these universities collaborate not only with each other, but also with the UK government, the EU, and the water industry stakeholders, which are mainly the water companies. So their focus is on using advanced analytical methods to improve water quality and infrastructure performance. I worked as a postdoc research associate at the University of Sheffield for about 5 years, and during that time I had the opportunity to contribute to several exciting projects that we had focused on using artificial intelligence to predict failures in water systems. So I'll some of these projects are listed here. I'll highlight a few examples to give you a general overview in the next slides of these projects and why they're being carried out at universities. So one example is the IntoTrack project, which was part of a larger European initiative called Shift to Rail, funded by the European Union. The focus of it was a vast project, and a bit of it was done at Sheffield. The focus of the Sheffield team was to develop data-driven solutions for Network Rail. Network Rail is the organization responsible for managing the UK's railway infrastructure. So it's the railway company. It's not a private company. It's under the government. So we developed data-driven solutions for Network Rail to estimate the risk of failures related to weather conditions, especially rainfall and the condition of railway drainage systems. So Network Rail, the issue is that Network Rail incurs millions of pounds of penalties every year to the train operating companies. So the train companies are private, who in turn must compensate passengers for delays caused by various types of failures, and a big part of these failures are weather related and due to poor drainage conditions like track flooding. So Network Rail provided us with the historical data of the condition of their system, the drainage systems, the railway, and their assets. And we applied machine learning techniques to develop models that were able to estimate the probability of failures based on recent rainfall and drainage system conditions. So the drainage system conditions were data of the condition of the system collected by inspections, and they were like in scores in from 1 to 5. 1 was best, I think, and 5 was worst. And we had also data of rainfall. We had data of the drainage system, like pipes, culverts, chambers, and different things. And so we try to correlate rainfall to the failures, rainfall and condition of the drainage system to the failures. And yeah, the model achieved a predictive accuracies of in the range of 0.7 and 0.8, and Network Rail was happy enough with the result to begin using these models outputs to rank their assets and prioritize maintenance accordingly. So this is just an example that shows when track flooding at a specific asset, which was a section of railway, under what rainfall condition in the last 5 days before failure, or in the last 5 days, under what condition, under what rainfall condition the asset could fail. The risk of failure could exceed like a threshold, like 0.5 or 0.7, so they can decide how to use the results in their business. So another example is the CoUD Labs project, which was also funded by the European Union. It involved partners from several European countries. At Sheffield, part of our contribution focused on sewer condition assessment using image analysis. So specifically, we trained deep learning models to automatically detect common defects in sewer pipes, such as cracks, blockages, and joint misalignments. Here, why this was done, because traditionally CCTV footage from sewer inspections is manually reviewed and annotated by engineers. This process is time-consuming, costly, and prone to human error. As a result, many companies are keen to explore automated approaches for defect detection in their CCTV data. So to train our models, we use datasets from UK water companies, as well as a Danish open source sewer inspection database. The image shown here is an example of how our model was able to automatically identify pipe joints and obstructions CCTV images. And here you can see some other sorts of types of failures that were detected in images. So we trained our model, and then we use the model to predict or to identify specific kinds of failures. So the process was automated. This is just an example. The process is automated. So just goes over the frames of the image and analyze the image and identify if there is any sort of failures. So next example, another type of project commonly carried out at research institutions like Sheffield involves developing data-driven solutions directly for the water companies in the UK. This is to support their operational decision making. So it's a kind of research that the output is directly used in the business. One example was a project we conducted for Yorkshire Water, which is a major water utility in the north of England. Again, they provided us with detailed data from their drinking water distribution network, which is a really large distribution network, and asked us to explore the potential for predicting iron exceedance within the system. So they wanted to check the turbidity levels and, if possible, predict exceedance of iron in this example above their thresholds. I mean, the thresholds that are defined in the regulatory frameworks. So the data set included a range of variables from pipe characteristics and network connections to water quality measurements, a lot of data of water quality measurements. So using this data, we developed models capable of estimating the probability of failure. But failure here was iron concentration exceeding regulatory thresholds. So Yorkshire Water then used the model outputs to rank their network sub areas by risk level, by this risk level, and this helped them prioritize flushing in areas with higher predictive exceedance, and ultimately improving water quality and regulatory compliance. So this is just a screenshot of the system with the sub areas. So machine learning was used to predict failure of probability of failure, probability of exceedance of iron in the system, and then we ranked these sub areas based on the probability of exceedance, and they were happy enough to use this to do the flushings for only these parts of on this part of the network, the pipes here in these sub areas, the red ones. Right. So let's shift now to the consultancy side. Within the water industry, artificial intelligence is still largely viewed as a research activity. As a result, businesses typically don't develop data-driven solutions in-house. Instead, they often collaborate with universities and research institutions for such work. In practice, the industry primarily relies on deterministic approaches, particularly numerical modeling tools. So data is usually processed using conventional statistical methods, which are then integrated into these numerical models to estimate system behavior and support decision making. Let's go to the next slide. Okay, this slide shows an overview of what's being done in industry in the UK. Water bodies are managed by categorizing them into various types, and each governed by specific regulatory frameworks. So a few examples are here. These frameworks are primarily established by the government, largely through the Environment Agency, which is an organization responsible for environment in the government. And these examples here are defined for river water quality assessments, just a few examples. Then there are private water companies. So these ones, there are about, I think, about 25, 30 companies in the UK, which are responsible for delivering services to the public, and their operations are regulated and overseen by government authorities like Environment Agency. Then we have the consultancy firms. They support the water companies by conducting assessments. For example, they do assessments of the impact of water companies' pollutant loads on the downstream water. The water companies they have to demonstrate to the Environment Agency that their pollutant discharges remain within legal limits, and if these limits are exceeded, they are required to take corrective actions to comply with regulations. And these consultancy firms do the most of the job for them. So at Intertech, where I work, we are involved in a wide range of environmental services, and there are we do modeling for water industry, we do subsea cables, offshore renewables, and many other things. I'm a part of the water quality modeling. Not only I'm a part of the numerical modeling team, and we mostly do water quality modeling for the water companies. So our clients in this bit of research are mostly water companies across England, Wales, and Ireland, and we support them to understand and manage water quality in various environments like rivers, coastal areas, bathing waters, shellfish waters. So the process combines data processing with numerical modeling to simulate how pollutants move through water bodies. So to do this effectively, we work with a broad range of data. So the data bit, it includes catchment characteristics, rainfall records, pollutant discharge data. These data sets come from multiple sources, such as the water companies, the clients themselves, the Environment Agency, and also other organizations. So before modeling, the data goes through a detailed processing stage. We collect, clean, and filter it to ensure it's suitable for input into our models. We use hydrology models that estimate flow based on rainfall and catchment features, along with advanced numerical models that predict the resulting water quality. We also have a suite of data processing tools that help us manage and interpret these large, diverse data sets. So on this slide, you can see examples of types of the data we use. And in the next slides, I'll go into some more details on some of the key sources and how we use the data, what data we use in our modeling process. So our data comes from a range of sources. The Environment Agency provides telemetry data and water quality samples, which are freely available and is actually widely used in our projects. Clients also often supply outputs from their sewer network models, which we use specifically for the projects that they are involved in. We also source data from third parties when needed. For example, rainfall data from the Met Office, which is typically available for a fee. For modeling, we use a combination of commercial and in-house tools. Commercially, we use software like Mike by DHI or Delft 3D for hydrodynamic and water quality modeling. In-house, we have a suite of data processing tools. We have developed many tools primarily using Python and MATLAB. We process most of our geographic data using QGIS, and we also develop custom QGIS plugins to support specific tasks within our modeling projects. We also have our own numerical modeling tools for simulating river flow and water quality. So these are mainly built in Fortran, MATLAB, C++, giving us flexibility and control over model development and customization. So here, just two examples of model domains used in our river flow and water quality modeling. The first example is a relatively simple case, a short water course within a small catchment. The second one is a more complex, featuring multiple bifurcations and larger, more intricate network. Each domain, the modeling process is the same. Each domain includes the main water course as well as discharge inputs, primarily continuous and intermittent discharges from wastewater treatment works. We also incorporate the locations where water quality samples have been collected. These are mainly through the data archives from Environment Agency and are free. Also,
Dear Hassan, I think we have lost your share screen. Could you please share your screen again?
Oh yeah. I've lost my connection as well, I think.
Yeah, we have missed you for a couple of seconds, but now it seems that you have already taken back your role, and yeah, great. Now we have your camera, and please share your screen as well.
I'm not sure why.
Perfect. Now we have it both perfectly. Yeah, go ahead, please.
Okay. So, yeah. So I was saying that in our water quality modeling process, we integrate the data that we obtain from the client water companies about their pollutant loads to the catchment, and we also use sampling data from Environment Agency. We use survey data gained from clients and rainfall from various sources, and so we integrate different various sources of data, and process them, and use them to define the boundary conditions and do the water quality modeling. So all of the information feeds into the model to estimate both river flow and the concentration of water quality parameters such as ammonia, BOD, SRP, and so on. And then the model results are compared against relevant regulatory standards to assess whether the discharges from the wastewater treatment works may be causing any water quality issues downstream. Okay, now I want to quickly show a few examples of the data we use in our modeling work. On this slide, you can see a few screenshots of river basins and catchments across England. This data comes from the Environment Agency's open data platform, includes catchment boundary shapefiles, as well as information about the ecological status of river reaches. This one forms an important part of the spatial context of our modeling. And we use this information to define our model domains and understand the existing water quality classifications. So this slide shows a screenshot of the UK Centre for Ecology and Hydrology site. It provides the detailed catchment characteristics. The dataset includes information such as catchment geometry, area, slope, and other physical properties. We combine this data with rainfall inputs from other sources to estimate flow within the catchment using our hydrology model. Then the flow estimates will be used in the hydrodynamic and water quality model. So this is an example of the rainfall data that we use. It is actually rainfall is sourced from various providers depending on the requirements of the modeling project. Met Office is one of the key sources, which provides different types of data. We mostly use radar data, which offers a high spatial and temporal resolution. We also use gauged rainfall data, either from the Environment Agency or direct from the client water company, depending on the availability and project scope. Having access to multiple sources allows us to select the most appropriate data for a more accurate flow estimation in each catchment. So this is another example from the Environment Agency's database. This shows a database that archives the wide range of data sets such as flow time series, rainfall time series, and groundwater level data, all of which are heavily used in our projects. This image shows an example of river flow discharge data. These records often span 20 to 30 years and are available at various temporal resolutions from daily to like 15 or even 5-minute intervals. And these provide really valuable data for model calibration and validation. Then we have Also, we make use of LiDAR data provided by DEFRA, the Department for Environment, Food and Rural Affairs. So DEFRA provides this data again for free, and it's available as composite grids, typically at a 1 kilometer resolution, I think. So it offers a quite high resolution elevation information. We use this data, LiDAR data, to estimate channel characteristics such as slope, and also other things required for our numerical models. Okay, next, this slide shows an example from the water quality data archives we use to extract data for our modeling work. This shows the screenshots of the data in England. The data set in England is called WIMS, and the one in Wales is called NRW. These are really comprehensive sources of sampling data for hundreds of water quality determinants for many years, like from like a few years to 20, 25 years. They are sampling data of water quality parameters, and they cover a wide range of environments, including rivers, lakes, ponds, sediments, coastal waters, wastewater treatment works, storm tanks, many things, and more and more. Samples are collected at numerous locations across the UK, and yeah, making these data archives really valuable. They are freely available and support both the definition of boundary conditions in our models and also the verification of model results. So this one shows, for example, how many determinants you can see at a small region, which are mostly metals in the water. So time series of the sampling data of these are available for mostly for at least 25 years, I think. Here, as I mentioned earlier, we have developed a range of in-house tools to support data processing. For example, when working with the WIMS dataset, the National Water Quality Archive, we use a custom tool that streamlines the extraction and processing of water quality data. This slide shows a couple of screenshots from the tool's user interface, which is designed to run within QGIS, which is also an open source GIS software. So the tool allows us to efficiently prepare data for model boundary condition setup and for verifying model results against observed measurements. So we do a lot of processing on the data that we receive, and it takes actually the major part of the task is usually processing and preparing the data, filtering the data for the model, and then we just run the model. If you have good data, you will get good results. So yeah, in summary, water quality modeling at our company relies heavily on extensive data processing. We work with data from a wide range of sources, and each dataset plays a role in different stages of the modeling workflow, from boundary condition setup to calibration and verification of the model results. So in fact, yeah, the collection, preparation, and processing of the data forms the majority of the work involved in delivering reliable modeling outcomes to the clients. So I've shown examples of the data that we use and process in our projects. Now I'd like to give an example of the results that we obtain to assess the impact of sewage discharges. So this plot shows the estimation. This is just an example. It's not a real result. It shows the estimated 99th percentile concentration of ammonia in a watercourse, along with the regulatory framework limits, high, good, moderate, and poor water quality classifications. So these limits are defined by water authorities like Environment Agency, and we use all the data that we have and do the numerical simulation of pollutant load transport in the watercourse and estimate the concentration of the pollutant like ammonia here to see if the discharges from the wastewater treatment work has caused any changes in the concentration. If we, for example, in this case, the concentration has crossed the moderate level and the classification is poor here as a result of the discharge from the wastewater treatment work. So in this case, the water company has to provisions some sort of like storage tank to reduce the impact of their pollutant from the wastewater treatment source. So we designed a storage tank solution, and using that solution, the concentration drops to be at the high classification. So in this case, the Environment Agency will be happy, and they can continue their activity. There is also a clip here. So this clip demonstrates how we visualize the results using GIS platforms for source apportionment. So in this process, the effect of different sources, such as wastewater discharges from multiple assets, multiple wastewater treatment works, for example, is quantified and assessed, helping the client understand their individual contributions to the water quality issues. Okay, thank you very much for your attention. If you would like to discuss any of these topics further, please feel free to reach out. My contact details are here, and I'd be happy to connect. If you have any questions, please ask. Thank you.
Great. Thank you so much, Ehsan. Thank you so much for this very interesting presentation and for brightening up about these topics, which I, by myself, think that are very interesting. So that's time for asking our audiences. We have already some remarks and questions. If you agree, we could go to them directly. And meanwhile, I will invite the audiences who are willing or would like to share their comments or question. They can raise hands, and then we will go to them as well in turn. Ehsan, you could see in the public chat by yourself, or shall I start with reading some of them? Or you prefer you go ahead with those?
Yeah, that's fine. I can see one question in the chat box, right?
Yes, I think Jakub.
Yeah, how
Uh,
yeah,
yeah. Go ahead, please. Yeah.
how much did ML, which means machine learning, I think, help you instead of numerical analysis? Which one is better? Okay, it depends. Machine learning is useful you, when your system is complex and you don't have enough information about your system. So, for example, when the water companies in the UK, they have information that they want to do numerical analysis, and yeah, for example, for the water quality assessments, they do so. But if the system is complex, there is no hydraulic model available for the system, for example, for the river, for the catchment, and or for the sewer network or anything. And the information is not enough. For example, you don't have enough information. You just have some sparse data, and you have just historical data. You don't know your system, the underlying processes of your system. So in that case, you would go with machine learning with artificial intelligence. And this is in the UK. This is when the industry, the companies go to the universities and ask them to do that for them. But for the numerical analysis and the numerical assessments, they do basically go to consultancy firms. So there is no better one. I think when you have enough information and data of your system, numerical modeling could be the best choice. If you don't have enough information, you don't know your system, you don't know the underlying process in your system, then machine learning could be a better choice. So I can see just this question.
Great. Thank you so much for addressing this question, Ehsan. Jakub, if it's fine for you, that's fine. Otherwise, please let us know. Anyone
Yeah,
else? I would like to encourage everybody to share your comments or question with us. Perhaps meanwhile, I could raise some remarks with you and taking your insights, Ehsan. Well,
yes, please.
uh, yeah, thank you. Definitely, I will go to much more details in even next round. But I think that, do you think any room for our, let's say, industrial stakeholders in Iran to take parts in such projects as well? Because, for example, we have lots of problem with data availability, and
Mhm.
I have seen that you had already working with lots of the, let's say, data sets, but in Iran this is not the case. So do you
Mhm.
see any room for going further or taking some further steps here in Iran for this kind of the projects?
What uh, analysis uh, and the system element?
Hassan, can you hear us? I have not your. Okay, we do not have you. It seems that we have lost you. Huh? Okay, it seems that we have lost Ehsan for a couple of seconds. So meanwhile that we will have him again from our audiences. Is there any question or remarks that you would like to share
No,
with Ehsan? Ah, welcome back, Ehsan.
sorry, I don't know what happened. I think it
No
yeah,
problem. No
just
problem.
dropped the connection.
Yeah, it could happen.
Yeah, I was I don't know if you yeah I was answering your question.
Yes, go ahead, please.
Yeah, the question was about if there is any room, if I see any room in doing such in Iran. Short answer is yes, I see room.
Mhm.
But
Perfect.
the issue is, for example, in the UK, why the water companies industry do these for example, detailed water quality assessments, for example, or the assessments on the impact of the pollutant discharge, impact of pollutant discharge laws on the environment, on the water, why they do this detailed analysis. The main reason is that the water authorities like the Environment Agency, the government, push them to do so. They have really strict rules to
Mhm.
maintain the quality of the environment. So the water companies have to do so. Otherwise,
Okay.
yeah. So if there is, this is one side of the issue. The other side is the infrastructure. So, for example, you mentioned the data unavailability. Yeah, that's an
Mhm.
issue. If you want to do assessment, environmental assessments, you have to have sufficient data and information about your system. Here in the UK, for example, the water quality data, the sampling data, the water quality data archives, they have been live for about 20-25 years. So they have started like sampling water quality parameters, like maybe 500 different parameters in many locations, in rivers, the coastal areas, ponds, lakes, everywhere. They sampled the water quality parameters every day or a few times a day. So they have a rich data set of the water quality parameters across the whole country. So, and it's freely available. But we can just use the data. I mean, without this data, it's almost impossible. So, yeah, the other side of the issue is the infrastructure.
Okay, thank you so much. Great. I'm just waiting for receiving any other remarks or question from our audiences. Perhaps if you agree, I could go a little bit further and ask my second question. This the package that you have just shown us about the water quality. It has been developed by your company at Intertech, or could you
Yes.
please give us more detail about it?
Yes, the screenshots of the tool, of the user interface of the tool that I just shown. Sorry, my camera is off.
Yeah, and the clip that you shared with us.
Yeah, let me turn
Yeah.
my camera on. Sorry, it was off.
Yes, please. No problem.
Yeah,
And if you would
yes,
like,
it
you
was.
could share your screen again with us as well.
Oh yeah. So this one, yes,
Mm-hmm.
it's been developed in house, so by us.
Mm-hmm.
It is specifically, it was initially designed to process the WIMS data, the England's National Water Quality Data Archive, the sampling data, and then we extended it to include other data sets like the the water quality data archive in Wales, and also the data that we receive from some of the companies, some of the larger water companies like Thames Water and Yorkshire Water. And yeah, it is a plugin actually in QGIS. So QGIS is a free GIS system, and the tool extracts the data and loads them, creates databases from the data, and then do specific filterings. Like if you want to filter your data by area, there's just one example here. If you have a catchment, you want to get the data of that catchment, or no, if you have a large region and you want to pass data of the entire region, it extracts data, filter it, and then do some further filterings for based on, for example, the type of the data, type of the site. Each of these circles shows a location where data is available, for example, and different colors shows different types, like if it's a river or if it's a wastewater treatment work output. So again, it can filter the data based on the type of the data. It can filter based on the determinants, based on the sample size, based on the. It can filter also the duration of the data, and then it will give you statistical. It does statistical analysis and process the data, finds outliers, gaps in the data, and filters it, and then eventually you will get the cleansed and filtered data that you want to use in your numerical model. And why this has been done in-house? Because such a tool didn't exist, and the company, because these data archives are used in various parts of the company, like in coastal modeling team, river modeling team, and other parts. So they decided to centralize this usage and develop a system, a tool that can centralize all of them and filter the data that in a way that you need in your modeling process.
Great, thank you so much. And perhaps a little bit further, well, this package is not open source, am I right?
No, it's not open source.
No. Yes, and the other is that, where the data comes from, it's from the field measurement, it's from the IoT or digital twin, or it's the combination of these techniques?
This data, the WIMS data, for example, the water quality data archives, they have sampling data. The data is sampled, so like sampling devices, like every day, or there are gaps in the data, but they do it depending on the determinant, on the type. They collect data every day or every week, I don't know, from that point of the river. So for many years, for 20, 30 years. So you have the data at the same location, sampled every day, for example, ammonia in many different locations. So
thank you so much for thank you so much. That was great. Well, Jakub wrote that thank you, Dr. Kazemi, best of luck. He wishes you best of luck. And we have received from Mason, thank you for your presentation. And Jakub later shared that he thinks that the most important obstacle in Iran is the lack of data. Perhaps that's not far from the reality as well. And we have just received a comment from Shayan. Thank you for your excellent and insightful presentation. Okay, it seems that everybody is happy with your presentation, and more remarks rather than question. It shows that the presentation was quite clear and let's say, brightening for them, for me as well. Yeah, so with that, I think we have already, let's say, encouragement and engagement from the audiences, and we could wrap up the session. Please, as a custom, at the end of the session, we will take the group photo. So I will invite those attendees who would like to do so. Please join us, turn on your camera, and then I will ask Mrs. Bakhshande to take the snapshot of us with the group photo, please. Yeah, I think that we have already some other Iranians audiences like Felix and Mark. So it was a pleasure to have you as well. Yeah. Okay. I see that Mojtaba also is joining us, perhaps somewhere at the middle of his way in the car. Perhaps. Good. Okay. Great. Okay, I see some familiar faces like Mason, like Shayan. Good. We just wait a couple of seconds to see if others are joining us. Okay. Okay, there are some new faces like Said. Welcome to our session also. Yeah. Okay. It seems that now we are stable in the joining number of the attendees to us. So I will take by myself, but Mrs. Bakhshande, please take a snapshot as well. We could count down. Okay, Yakub also joined us. Okay, we could count down. 3, 2, 1. Great. Well, I have forgotten to look at the camera, so I will just repeat the counting down. 3, 2, 1. Great. Thank you so much, everybody, and thank you so much, Ehsan, for your time and sharing your insights and knowledge with us. It's really appreciated. I also appreciate the audience's time and attending. Yeah. Thank you so much. Ehsan, do you have any comments or would like to share us with us?
No, I
Any
just
more
wanted to
comments?
thank you for inviting me, and it was a great time to talk for you and the other friends, and I hope it has been useful.
Sure, it was, and we thank you for sharing your time and knowledge.
No problem.
Great. With that said, let's say goodbye and have a nice day, everybody.
Thank you. Have a nice day.
Bye
Bye bye.
Thank you. Bye bye.